So I think in the last class we were discussing about the concept generation, and more importantly we talked about perpetual motion machines, which are machines that cannot be realized. And we have also seen the laws which prohibit the possibility of perpetual motion. The law of thermodynamics. We will be studying about these laws in detail later, but these laws, they give a scientific explanation why a perpetual motion machine is not possible. Today I will be making again a detour from my regular routine lecture. I think in the last class also you had a discussion on the various product teardowns that happen in the design appreciation lab. Again today I will be making a small detour. This is to facilitate or give a perspective for the assignment that we are going to, the term assignment that we are going to work on. The term assignment will be given today, and I'll explain about the term assignment later. Okay, what we are going to discuss today is an idea called design for strength. We are going to discuss something which is called the design for strength. Now for your rest of mechanical engineering, you will be studying at least 3-4 papers, which is in a way deals about the designing for strength. You will be studying a paper called Strength of Materials, which enables you to design for strength. We will study a paper called the Design of Machine Elements. We will study another course on design of transmission systems, and also we will study another course on finite element method. All these courses are meant to enable you to achieve this, what is called the design for strength. Now basically let me put a question like this. Suppose I design a building. The functional requirements are given. We have arrived at the technical specifications. We have designed the building. See, one thing about designing a building is laying out the structure. Like for example, how big the hall is to be. Okay. Or where to have the hall, where to have a veranda. If you are building your house, okay, you have to design where to have the kitchen, where to have the hall, and what should be the size of the hall, what should be the size of the kitchen, where to locate the toilets and bathrooms. So this is the schematic arrangement of the various requirements. Now in this hall I should decide how big the hall is to be. And there are many other important things. I would prefer to have my hall not as rectangles, but a sort of trapezium. That way the communication, everything will be easier. See, this is a rectangular hall. Okay, given a choice, I would prefer a hall which is a trapezium. Because that way communication will be easier, visibility will be easier. When I am standing and then viewing, I am not able to see people sitting here or there. Because my view is something like a cone. Okay, I am not able to view all. I am not able to see this diagonal cutting off. I am not able to see the persons here. Similarly, I am not able to see the persons here. So I would prefer a hall which is trapezium in shape because that coincides with my vision. And similarly, the same is true for people sitting in the other side also. For that also it will be convenient if the hall shape is slightly changed. This is left to the architects. Primarily architects do this job. Now we are going to take up a slightly different aspect of design. Namely, suppose I have decided this is going to be the hall, this is going to be the everything. I want to decide what should be the cross-sectional area of the column. There is a column coming over there. What should be the cross-sectional area? In that cross-section, how much must be concrete and how much of that area must be steel? This is an important issue that is to be sorted out. This is designed by, this decision is taken by who is known as a structural engineer. Or let me take Take another example. You are sitting on a chair. You are sitting on a chair. Suppose, take the steel chair. It has an extruded steel tube which is bent. Is it okay? What should be the diameter of the tube and what should be the wall thickness? This is another important design decision which is to be made. Do you understand? You are sitting on a chair, and what should be the tube diameter and what should be the wall thickness of the tube? On what basis do I decide this? This is an important design requirement. Suppose you have the controversial Kudangulam power project has come up. Yes? Okay, the system is going to reach criticality in another, say 1 month or 2 months. Let's not go into the debate whether it is good or bad. Okay, opinions may differ. But suppose it is a 100 megawatt power plant. There is going to be a steam generator which generates, a steam generator is a boiler, which generates steam. The steam generator is going to generate the steam. That steam is going to forget about the nuclear part. Okay, that is controversial, so let us leave it aside. There is going to be a steam generator which generates steam, a boiler generating. It is no more called a boiler because in many of the modern boilers within port, there is no boiling taking place. You understand? What is boiling? You see water boiling in your house. Okay, you keep the water in a vessel and then switch on the stove, then the water boils. That sort of boiling never takes place. The temperature is so high, it instantaneously goes to vapor. So people object to us calling a boiler a boiler. It is no more a boiler, rather it is called a steam generator. See, words do matter. The terminologies, they do matter. When no boiling is taking place, how can I call it as a boiler? It is meaningless. But at the same time, the word terminology is strict, so we have to make a compromise. We should understand. When I say steam generator, you should not be thinking of something else. So there is a steam generator which is generating steam. That steam is sent to a turbine, where the thermal energy of the steam is converted into mechanical energy. From the turbine, what happens? How does that happen? From the turbine, the mechanical energy is delivered to a generator. Okay, an electrical generator, so the electricity is generated. How do I deliver the mechanical power to the generator? Beautiful. Very well said. The mechanical power is transmitted through a shaft. Okay, what should be the diameter of the shaft? Let's forget about everything. You have a 1000 megawatt power plant. Okay, you have a turbine generating power. That power needs to be transmitted to a generator. It is to be mechanically transmitted. There is no other way of doing it. The rotary motion of the turbine needs to be transmitted at a particular speed and particular torque. Now what should be the diameter of the shaft? How to decide that? So I have told the power generated is 1000 megawatt. The shaft is supposed to transmit a 1000 megawatt power. Please tell me, can you guess what will be the diameter approximately? Roughly. Plus or minus say 10 mm, 20 mm, 30 mm, plus or minus 30 mm, plus or minus 100 mm. Roughly. Will you think? The diameter itself will be in meters. At least that much is good. Diameter will be in meters. It will be around 2.53 meters diameter. The diameter of the shaft transmitting power will be around 2.53 meters in diameter. So now, whether it is 2.5 or 3, how to decide? On what basis will they decide whether it is to be 2.5 or 3? So these decisions are to be made by performing what is called the design for strength. And that is what I am going to talk for the rest of the 20 the rest of the lecture. And probably I will discuss a product and then I will talk about the assignment. Is it okay? I am not going into, please believe me, my objective is not to teach you the whole design for strength. Because as I told you, that is about 3-4 courses altogether. So I am not going to make you experts, because at the end of the lecture, please don't ask me, sir, how do I arrive at the diameter of the shaft at Purangu? No, my objective today is much more humble. Okay, I will tell you how the problem can be approached, specifically, exactly how it is done. You will be learned through the different courses, okay, during your study. Right? Next slide. Now, there is one basic law which I want you to remember very thoroughly. Whenever you talk about the design for strength, the basic law is the stress induced is less than or equal to the permissible stress. The basic law which we should worry about in design for strength is the stress induced is less than or equal to the permissible strength. Let me explain what this means. Every material, they have, basically the materials are classified into 2 categories. Yes, can somebody say? Materials are categorized into 2 categories. One is brittle materials, the other categories are ductile materials. Brittle, ductile. Can you give an example of a brittle material? Glass is a brittle material. Any other example of brittle material? What? Ceramics. Okay, ceramics are brittle materials. Any other material which is brittle? Any other material which you can see around which is brittle? Yes, somebody said that? Brick is a brittle material. Concrete is a brittle material. Rock is a brittle material. Can you give me good examples of ductile material? Steel, copper, gold. Gold is an excellent ductile material. Aluminium is ductile material. Good. Okay, now let us go back to what is the difference between a brittle material and a ductile material. Can you please say what is the difference between the last person at the corner? Yes, sir. You too. Can you please tell me what is the difference between a brittle material and a ductile material? See, I have been talking about brittle materials and ductile materials. What is the difference between a brittle material and a ductile material? No, sorry.
Drawn into wire.
So that is the definition. A brittle material can be drawn into wire. A ductile can be drawn into wire. So that is a definition which you have studied in schools. Fine. Now let us learn the engineering definition of this. A brittle material is a one which can be deformed drastically. They give rise to 2 families of materials. They give rise to 2 families of materials. One family called the brittle material, the other family called a ductile material. Now let me go to the next slide. Let us see next. Let's see what happens typically. This is a slide I intend to use later, but I want to use it for some other purpose. Here is a material, a rod. The rod is fixed at one end. It is pulled in the other. Okay. Now the loading continues even beyond the elastic limit. You can see some plastic deformation taking place, some permanent deformations taking place. This is a typical example of how a low carbon steel rod will fail when you load it like this. You will be doing these experiments. A typical low carbon steel, all of you will be doing these experiments. A typical low carbon steel fixed at one end, pulled at the other, will first plastically deform and then finally it will break. So prior to failure, there is some plastic deformation. Prior to failure, there is some plastic deformation. Such failures are called ductile failures. These ductile failures are relatively better for us because they give you a warning. They give you a chance to know something is going wrong, it is going to fail. On the other hand, brittle materials, they don't undergo any plastic deformation prior to failure. All of a sudden, without any warning, without plastic deformation, brittle materials fail. So, if you are using a brittle material, you have to be doubly careful. On the other hand, if you are using a ductile material, okay, they undergo what is known as a plastic deformation, and this particular phenomena is called yielding. Okay. The ductile materials, they undergo a particular phenomena called yielding. What is yielding? Yielding is small amount of increase in strain even without an increase in stress. If you see the traditional stress strain diagram, of suppose if you take a typical low carbon steel, you have the stress plotted in the y-axis, you have the strain plotted in the x-axis. For a low carbon steel, the curve will be something like this. It will be almost a straight line. So it goes, as the stress is increased, the strain also increases. So at this point of time, you see something funny happening there. If the stress increases, the strain also increases, you don't have any objection. That is a very normal behavior. The stress increases, strain also increases. The load is increased. What is stress? The load per unit area. Strain is increased in length per original length. So stress increases, strain also increases, there is nothing to worry about, it is a normal behavior. But on the other hand, at this point, the stress doesn't increase. You see the y-axis doesn't increase. In fact, it slightly comes down. But on the other hand, what happens to strain? That is a very dangerous phenomenon, is it not? I am not increasing the stress, but still, what happens? The strain is increasing. It keeps on deforming. It begins coming. So this particular point is called the yield point. This particular point is called the yield point. It is as if, it is a very poetic word, it is as if the material, it resisted up to a certain point and then it started yielding to it. In English you say, don't yield to his pressure. What is it? Don't yield to his pressure. What is that? Don't give way. Don't give pressurize you, but still you resist. The material, this point, is referred to as a yield point. I elaborate on this because this you must remember always. This particular point is called the yield point because the material resisted up to a certain level and after that it has started giving up. The material has given up all hope. It has started yielding to the pressures. So that particular point is referred to as the yield point. So for all materials, now the material can take up some more load. The material is breaking up only at this stress. For all tactile materials, okay, the material is loaded only up to the yield point. Tactile material, the material is loaded up to the yield stress. For all tactile materials, the material can be loaded up to the yield stress. I don't want to load beyond this because beyond this the material behavior is not very dependent. It has given up already. So I want to load it only up to the yield stress. Now for a brittle material, I will load ultimate tensile stress. Let me draw a graph for the yield, graph for a brittle material. Have you understood? Anyone is having any doubts? Sir, only the doubt. Last person. Next. Huh? Have you taken down this? Okay. Yes.
So this graph is for ductile material.
This graph is for a ductile material. This graph is for a ductile material. The example is low carbon steel. This graph is for, have I made a mistake? This graph is for a ductile material which is a low, example is low carbon steel. Okay. The graph I have drawn is specifically for a low carbon steel. For aluminium it will be slightly different. For copper it will be a little more different. Okay. But essentially it is for low carbon steel. Is it okay? Any doubts? Now, I will go to a brittle material. See, one of the examples of brittle material is cast iron. Cast iron is a brittle material. Grey cast iron is a brittle material. Let me not say generally cast iron. I am very specific. There is a particular category of cast iron called grey cast iron. Okay, you would have seen grey cast iron in many, all the machine tools. Lathe bed is made up of grey cast iron. All the casings, or most of the casings, are made up of grey cast iron. Now, if you draw the stress strain curve, the stress strain curve for grey cast iron. Okay. That's all. Even this curve will not be seen in many cases. As stress increases, strain also increases. At one fine point, just like that, it breaks. Just like that, it breaks. And this point is called the ultimate tensile strength. If it is a ductile material, you will load it up to the yield point. If it is a brittle material, you will load it up to the ultimate tensile strength. These properties can be obtained from the internet. We have data books for all materials. If that material is going to be mechanically used, the first thing they have to do is they have to conduct the stress strain experiment. There is something called the universal testing machine. There are international standards available. As per the standard, you prepare the specimen, load it in the universal testing machine, conduct the tensile test. This particular test is called the tensile test. You determine the yield point. If it is a ductile material, in brittle material, it will not yield. Yielding is associated with plastic deformation. Okay, yielding is associated with plastic deformation. In brittle material, there is no yielding taking place. So you have the ultimate tensile strength. Is it okay? Now, again, if the yield point of the material is say 300 megapascal. For example, for typical low carbon steel, the yield stress is 300 megapascal. For low carbon steel, okay. For a typical low carbon steel, the yield strength is 300 megapascal. Okay. Suppose, if I say that the low carbon steel is the material for the frame of your chair, if I say that the stress induced in the leg is 300 megapascal as of now, will you be sitting comfortably? Okay. So what do you need? The stress induced must be much less than 300 megapascal. And how do you achieve this? You achieve this by resorting to what is called the factor of safety. You understand? If I say that the stress induced in the steel rod, the steel tube on which you are sitting now is 300 megapascal, immediately everybody will stand. They don't want to take the risk. So we decide if the ultimate tensile strength is 300 megapascal and if the factor of safety, is it understood clearly? Now, and I want to have a factor of safety of 3. Factor of safety is given by the symbol n. N is equal to 3. The factor of safety is 3. Now I arrive at what is called the design yield strength, which is yield strength by factor of safety. This is 300 by 3, which is 100 meters. That is, the material can actually withstand up to 300 megapascal, but I don't want to take the risk. I want to limit the stress coming to be less than 100 megapascal. Why? Because I want to be safe. In my design, I want to be safe. See, I told you an example, I just want to recall. There was a cliff like this. Okay, there was a person standing here. Okay, will you go up to this point? See, science tells me very clearly, only if we cross this point I will fall. Science tells me very clearly, only if we cross this point, and to be more precise, only when the high center of gravity crosses this point, I will fall. If the center of gravity is well within this, I will not fall. This is what science says. But will you go up to this point? No, I will not. I will try to stand here, peep and then see. Even if I am curious, I will never go. What determines this distance? The amount of safety that you would like to have. Probably my father will stand here and then try to see. He is more conservative. My son probably might like to go here, stand and see. He is more adventurous. The attitude of the designer determines the factor of safety. Do you understand? It is not only the decision about when his design is determined by the designer. It is the attitude of the designer. All British designers, I can tell you, all British designers, they use very high factor of safety. That is in their national mentality. They are very conservative designers. All Japanese designers, they are more adventuristic. They use very less factor of safety. So, factor of safety, it depends on how much you want to take risk. So, this decision is purely that of the design. Okay, if you are very confident of your calculations, okay, then you can reduce the factor of safety. When you are not very sure about your calculations, then naturally you tend to put in more of factors. You understand the idea? Now this is for what material? Generally, this is for ductile. For brittle material, the design ultimate tensile strength is, can somebody say? Anti-chemical. So this is how you arrive at what is known as a design stress. Can we go back? Two slides. Now, this is where the basic law of design for strength comes, which says very clearly the stress induced is less than or equal to the permissible stress. This is what the permissible stress is. So what is the basic rule governing the design for strength? There is some stress induced in the member that must be less than or equal to the permissible stress. Shall I proceed further? Now, next slide. Now, what are the types of stresses that I can anticipate? What are the various types of stresses that I can anticipate? I can basically anticipate, okay, there are basically three types of stresses. One is a tensile stress, the other one is a compressive stress, the third one is a shear stress. Okay, my objective today is to make clear what these three stresses mean. My objective today is to make clear what these three stresses mean. Some special cases we will discuss them later. Next slide please. A tensile, tensile loading. Okay. You have a rod, you fix it at one end, pull it down. Okay. You have, say, a rod like this, pull it out on both ends, something like this. You have a rod, you pull it down at both ends. These are typical examples of a tensile load. Is it okay? Now there are many situations in which you subject materials to a tensile load. Now I have a bag Imagine this to be a load. Okay. What is, by the way, the load-bearing material in human body? Load-bearing elements. So it cannot be a single thing. Bones. Okay. The structural member of human body is the bone. Now I am carrying this bag. What is it doing to my elbow bone and my this particular bone? The bone is it subjected to tension? Is it subjected to compression? The bone, my elbow bone is subjected to, it is stretched. Are you able to visualize it? Okay. Now, I am a weightlifter. Okay. I am carrying a huge weight with the same hands. I am carrying a huge weight in my hands. Now, what is this weight doing to the same bones? It is subjected to, are you able to visualize? I don't see many bright eyes around. Okay, when I am holding it like this, my bone is subjected to? Sure? But when I hold it like this over my head, my bones are subjected to? Are you able to distinguish between the two? Okay, let me take up some not so obvious cases. Let me take up some not so obvious cases. Suppose this column of this particular building, what type of stress is it subjected to? Sure? The column of this building is subjected to compression. Okay. The chair in which you are sitting, yes, you are sitting very comfortably. What type of load? Yourself only. Yes, please stand up. Sir, உங்களுக்கு பக்கத்துல இருக்காரு நீங்க தான் சார் ஏறீங்க. நீங்க ஏறீங்க சார். நீங்க What is the type of the load the leg of your chair is subjected to? Huh? The leg of the chair is subjected to compression. Can you, by some modification, subject the tensile load to your chair? I want to subject the leg of the chair to a tensile load. Can I do it?
Swing.
Yes, please sit down. Yes.
Swing.
Yes.
Stand up. Swing.
Pardon?
Hang away.
That is hang the weight. You hold the chair in your hand and then hang the weight. Possible?
Swing.
Okay. One person is holding the chair. Okay. Here, and the other person is holding the leg and then pulling it. Okay. Will induce a tensile. Okay. You are sitting on a swing. Okay. There is a rope which is attaching the seat to the tree. When I am swinging in the rope, what type of stress is induced on the rope? Sure? Is it okay? You are using your accelerator. The motion is transferred to the carburetor through what? A cable. When I am applying my accelerator, what is happening to that cable? Who are all saying tension? Good. Who are all saying compression? I'm sorry. Okay. Please believe me, a cable or a rope can never take up a compressive load. You get my point? Can a rope take a tensile load? No. Yes. Rope can take a tensile load. I'm happy you are awake. But can a rope take a compressive load? Can a rope take a? No. A rope cannot take a compressive load. Similarly, a cable also, under normal circumstances, a cable also cannot take up a compressive load. A cable is always meant for transmitting Tensile load. Okay. What? Do you have an objection? Spring? Can be either. There is something called, I'll come to you. There is something called a tension spring and a compressive spring. Okay, we will come to it later. I don't take up spring when talking about tension and compression because the stress induced in the spring ultimately, when it is, whether you apply a tensile load or whether you apply a compressive load, the stress, no please listen carefully, I am not asking you anything. The stress applied, primarily the stress applied to the spring material is shear. We will talk about it later. That is why I don't take up, see certain examples are not good examples. Since you have raised it, I am duty bound to answer that. I didn't take up springs at all. Because, whatever, whether you compress it or whether you subject it to tension, the type of stress induced is shear. We'll come to that later. First let us sort out the tension and compression. Here you are having a turbine blade, okay, a wind turbine blade. As the turbine rotates, what is happening to the material here? Say suppose I'm sitting here. What happens to the material here? Is it subjected to tension or is it subjected to compression? No, not at all. Sure? Why tension? Or shall I say, when this blade comes up, compression. And when it comes down, tension. Sure? Shall we all agree to this? When the blade comes up, see this is the blade which is rotating. Okay? This is the blade which is rotating. Okay, when the blade comes up, the material over here is subjected to, when it comes here, the material, absolute nonsense. Is it okay? Okay, when it is here, if you say it is compression, and when it is here, if it is tension, no. The reason is, I will tell you. Listen here, the reason is, you have a huge mass which is rotating at a very high speed. What will happen? What forces do you expect? You have a huge amount of the centrifugal forces, okay, and they will pull every element out. Okay, it will have like please, like you tie a stone in a string and then rotate it. What is happening to the string? Is it subjected to tension or compression? Sure. The same thing must happen to the blade also. Typically, no, the load is at the end, but here the load is thrown. Typically, do you know the diameter? All of you must know the diameter of at least some turbines. Can you say what is the typical diameter? Typical diameter, plus or minus 1 meter. 92 meters. A typical diameter, the typical length of the blade is about 40-50 meters. 40-50 meters. You can see blades being transported across GST road through huge lorries, you might have seen. A typical blade length will be about 40 meters. Okay, when it comes in a circle, it is about 80 meters. So, such a huge mass rotating will have a huge amount of tensile load acting. Now suppose you have a fan, we don't have a fan here, you have a fan which is rotating. What happens to an element in the blade of the fan? It is subjected to primarily tension. Is it okay? Now, have you understood tension and compression thoroughly? Is it okay? Shall we go ahead? Now, next. So this is an example of a compressive load. You have a typical column in which the column is subjected to a compressive load When I stand, my leg bones are subjected to compressive load. As you sit on the chair, the legs of the chair are subjected to a compressive load. Is it okay? Now, next slide. What is most interesting and difficult to comprehend is a shear load. As mechanical engineers and aeronautical engineers, you should have a very clear idea of what a tensile load is, what a compressive load is, what a shear load is. And when I give some instances, you should be able to tell whether it is a tension or compression or shear. Okay, suppose let me take two plates which are joined together by means of a bolt. You have two plates. Okay, I drill a hole. It is easy now. I drill a hole. I put a bolt. And then I join these two plates together. Now this plate is, the two plates are pulled apart like this. Now I am not imagining situations. Okay, I am not imagining situations. See, at the beginning of the class we talked about boilers. Is it okay? Now boilers are, how do you make a boiler? You need a cylindrical vessel. Imagine you need a cylindrical vessel. How do you make a cylindrical vessel? A sheet needs to be bent in the form of a cylinder and then you have to join it. One way of joining the two ends is by using a bolt. This is okay. I can bolt it and then join it. This is one way of making a cylindrical vessel. I have made a cylindrical vessel. Now if there is a huge internal pressure, how will it act on the bolt? It will act like this. If there is a huge internal pressure, is it okay? This will try to open up. So, this will pull in this direction, this will pull in this direction. Yes or no? So, I am not imagining something. This is something which is practical, which is realistic. Now, my question is, what is happening to the bolt? Is it subjected to tension or is it subjected to compression? Okay, now the bolt is subjected to actually a classic case of shear. It is neither compression nor shear. If you take the bolt alone and then visualize it, are you able to see? This is part of this. Now I am taking the bolt alone and then I want to see it. Now if you take the bolt alone and then see it, now you have, this is the bolt. Okay, forget about the head. Now this part of the bolt is pulled here, whereas this part of the bolt is pulled in this direction. Now at this section, the top is pulled in one direction, the bottom is pulled in the other direction. This is called a typical shear load. This is called a typical shear load. Now you have many such instances. You have a coupling. All of you might have seen different couplings. Okay. You have one, this is one flange, this is another flange. They are joined together by means of coupling. One flange and another flange are joined together by means of coupling. One flange is connected to the motor and the other flange is connected to the pump. Say, when it tries to rotate, what happens? One flange tries to rotate in one particular direction, the other flange is connected to a load, so it is not rotating so easily. What happens to the bolt? Again, it is subjected to shear. Do you understand? You have a shaft which is transmitting a torque. We have talked about Poodle and 2 diameter, 3 diameter shafts. What essentially happens here? The turbine, it tries to rotate the shaft, but the other end of the shaft is connected to where? The generator. So the generator is not letting it rotate easily, because there are magnetic fluxes and all that. So it is trying to hold it. So when the turbine side it is trying to rotate it, on the generator side there is some resistance to this rotation. What happens to the shaft? It is subjected to torsion. It is subjected to shear. So the third type of load that I want all of you to appreciate is the shear loading. So you know about tension, you know about compression, you know about shear. In fact, tension and compression are not two different things. Okay? There is a common terminology for that is called axial loading. Along the axis, see, if this is the rod, if this is the rod, if I pull it, it is tension. If I push it, it is compression. Is it okay? So, along both the loads, they act along the axis. So, the common terminology for this is axial loading. The common terminology for this is axial loading, because both act along the axis of the member. Both tension and compression act along the axis of the member. So the common terminology is axial loading. Is it okay? Now, so we have studied about axial loading and about shear. Now, if I give you a practical situation, will you be able to identify in what way it is loaded? Good, fine. Next slide, please. See, the other common failure modes there are few other common failure modes. Okay, I will just mention about these things. Okay, there is something called fatigue, there is something called creep, there is something called fracture, corrosion, wear. You should know about all these things. Suppose I give you a small wire. I give you a small piece of wire. Okay. Ask you to break it into two. I am not giving you any tools. How will you do it? Pull it. It is a steel wire.
Twisting.
Good thinking.
Twisting.
How will you bend? What? No, I want this answer because it is convenient to me. Okay, these are good. Rubbing on the ground, scratching the point at which you want to break, these are all possible. But this answer appeals to me. He says, if this is the piece of wire, he says, he will bend it repeatedly like this. I think that sounds to me to be the easiest way to break a steel wire. We can do many other things. Okay, you can scratch it on the ground and try to do it. But to me it appears, without any tools, to break a wire into two, the most intelligent way of doing that is bending the wire repeatedly. Very thin. I don't know. But wire can be bent like this. So what is it going to get? Like a thread. But my point is to break it. Okay. So suppose it is a 2 millimeter diameter wire. Okay. Typically what I am thinking of is there is a wire used for tying up things. Okay. So typically if you want to break that, you will bend it repeatedly this way. Now my question is, what happens? Why it breaks so easily? Can you pull it and break it? If it is a 2 mm diameter wire, can you imagine pulling and breaking it? Or compressing it and breaking it? Can you do something like this, some shear and then break it? No. But when I apply it, when I repeatedly bend it this way, that way, probably 5-6 times, it breaks. Now there is a beautiful phenomena called fatigue. Okay, please don't confuse it with the mental fatigue that you may encounter now. Okay, this is a mechanical fatigue. What we are referring to now is a mechanical fatigue. Fatigue is something, when I say fatigue, you should say immediately cyclical loading. Fatigue means cyclical loading. It is worth loading down. Fatigue means cyclical loading. Now what I do is, in pure tension, the material doesn't give up. In pure compression, the material doesn't give up. But when I subject it to alternatively tension and compression, the material fails much more easily. When you subject a material to tension and compression alternatively, the typical stress versus time curve will be something like this. Stress versus time. The stress doesn't remain constant with time. The stress keeps on varying with time. So, a typical stress-strain curve, not stress-time curve, in his suggested method is this. Okay. When I subject materials to cyclical loading, the material fails much before what? Much before the ultimate tensile strength or the ultimate compressive strength. Now this particular phenomena is called fatigue. About 60% of all the failures taking place are failures because of fatigue. You take any component that has failed mechanically. You take all such components. You can say 60% of failures would have taken place because of fatigue. Now, does this happen? Does this happen in real life? Does the load change over time? Can somebody give me an example?
Boilers.
No, wait a minute. Let me phrase the question first. Can somebody give me an example where the load, the type of stress at a particular point, it keeps varying over time? The beams? No, how does the load vary over time? I am standing above a beam. Okay, there is a beam here. So exactly I am standing above a beam. The load remains constant. But please believe me, it is not. I may walk off anytime and I may walk in anytime. After half an hour, nobody might be in this hall. So the beams will not be subjected to the same amount of load. But still, beams are not subjected to fatigue loading in a rigorous sense, because there are many other forces which remain constant. But please remember, the point I am trying to make is, the load doesn't remain constant as it appears. Any other better example? Beams, yes, but still, it is not very rapid variations.
Bridges, sir.
Bridges, okay, good. Bridges, water tank. How does the load vary? When the water is full, there will be some particular stress. Good, but it varies with a long period. I want to say something which is very quickly. But plane, aeroplane, what does it mean? Very good. While flying, the wind forces, they don't remain constant. The wind forces acting on the wings, they do vary, but not complete reversal. Not complete reversal. What was a point which was subjected to tension may not be subjected to compression. But lift. Which part of the lift? And there are many parts in the lift. Chair which is Is it a chain?
Cable.
It is a cable. There is a cable attached to the lift. Okay. So that is subjected to very good thinking. That is subjected to load which varies continuously. But will that cable ever be subjected to compression? By law, no. By law, a cable cannot be subjected to compression. It should be tension varying over time. It should be tension varying over time. Any other example where a mechanical member is subjected to varying loads?
Railway compartments.
What?
Vehicle suspension.
Vehicle suspension. I am bothered with regard to springs. We will come to springs later. Good thinking. Okay. Let us not go to the helical springs. Let us go to the
Trains.
1 minute. Let me finish it and then come. Let us go to the flat plate springs called leaf springs. These are used in heavy vehicles. Okay, lorries. Okay. As they vibrate, they undergo varying stresses. Yes? Cranes. Train.
The cable used in the cable that.
Okay, cable used in a crane, similar to the lift. Good.
Trains.
No, I want two railway compartments joined together.
Coupling part.
Coupling part. Fine. What happens to it?
When it stops, they get compressed and.
Okay, when the vehicles stop and if there is a small pollution, there are two shock absorbers which take up the load, but the coupling which joins them is always subjected to tension. It may get relieved at some point of time. Now, can you tell me where a mechanical, there are thousands, believe me, where a mechanical member, thousands, I mean millions, okay, believe me, mechanical member where a complete reversal takes place, or at least the load comes to zero and then it varies. Okay, let me give you a few examples. Okay, I have asked dinner. Please tell me when I walk, what happens to my leg bone? That is the sexual member. You only have said that is only supposed to take on the load. My entire load of 100 kg is taken by my leg bone. What happens to this leg bone? Subjected to compression, but when I keep on walking, now at this juncture, what is the load taken up by this bone? Huh? Almost zero. Is it okay? I am referring to the leg bone. So please listen here. I think we are transacting something very, very important. Okay, I am not joking or I am not mimicking, I am not playing any act. This is some serious engineering. Okay, listen carefully. Now when I walk, please tell me what happens to this bone. Okay? Okay. Right at this position, there is no practically any load acting on this bone. But when I do like this, it is subjected to almost 1 kilonewton. If my weight is assumed to be 100 kg, it is roughly 1000 newtons. Please believe me, the dynamic load, we will come to that part later. The actual load subjected to the bone is about 3 times my weight. We will study about it later, how that gets magnified and all. The actual load experienced by this bone when I walk is about 3 times my weight. And when I run, it is going to be 5-6 times my weight. Because of the dynamic effect. We'll talk about it later. But simple static walking, very slowly and keep walking, the load induced is maximum compression. So can you appreciate that the loading curve experienced by my bone is something like this. Stress versus time. It is always in the compression side. Am I right? And does this happen very in quick cycles or in more long cycles? It happens in quick seconds. Can we think of few other examples? Cycle pedaling. Which part are you? Please don't refer to a human system. I didn't talk about human body taken in its whole complexity. I am talking about a simple component. That only I can do some analysis. Pedal. Yes.
When you pedal forward.
Okay. When you pedal, okay, you pedal only for past a circle. The remaining cycle, the pedal is not subjected to any compressive load. Good. Very good. Then, he talked about cycle. Okay, door hinge we will go to it later. He talked about cycle. Why don't you explore some other parts of a cycle? Yes, sir. Can you explore some other part of the cycle? அடுத்த ரெண்டு பேர் நான் ரெண்டு பேர்கிட்ட பேசிட்டு வந்தேன். அடுத்த ரெண்டு பேர் பக்கத்திலே இருந்ததுனால அவங்களுக்கும் இன்ஸ்பயர் ஆயிட்டாங்க. சொல்லுங்க. Can you tell me a mechanical part which is subjected to? Soldier sir. Can you tell me a mechanical part which is subjected to varying flow? No, what are we talking about? We are talking about loads that vary over cycles. Loads that vary over time. You know, believe me, most of the members, they are subjected to. Can I have the time, please? 12:20. So, there are mechanical members which are subjected to. I'll be overstretching myself today. We may have to, for the time wasted, I have to compensate. So we may have to work for another 10-15 minutes. More than 12:40. Okay. Those who are not happy can walk out. உச்சி செல்லாம் இங்க சொல்லக்கூடாது. இல்லைன்னா கிளம்பி போயிட்டே இருக்கலாம். The point is, there are materials subjected to cyclic loading. There are many examples. Somebody talked about bicycle. Imagine what happens to the stresses on the spokes. I told you already, the spokes are mechanical members which are putting tension. Pre-stressing. Good. If they are pre-stressed. But what happens when some compressive, when the spokes come to this particular position, this is the wheel. When the spoke, this is the half, or even visualize. When the spokes comes to this particular position, it takes up all the compressive load. So it is already subjected to tension. So what will be the typical loading pattern? It will be something like this. If my pre-stress is correct, okay, when it is not taking up any load, it is subjected to tension. When it is taking up all the compressive load, part of the tension will be neutralized, and then it will take up some compressive load. Or it can be something like this also. I don't know really. I may have to measure stress versus time. Stress versus time, I don't know. What happens exactly? I may have to measure and then find out what happens exactly. All that I am trying to drive at is mechanical members are subjected to varying stresses over time. Stress that varies over time. This particular type of loading is called fatigue loading. Since 60% of mechanical failures are by fatigue loading, it is very important for us to learn and study about this particular method of failure. Next is creep. Next is creep. See, generally, you load a member, release. You expect the strain to remain constant. The stress doesn't vary. So the strain also, after that the strain should not vary. But what happens in certain materials, the strain, it varies over a period of time. In certain materials, the strain varies over a period of time. This particular phenomena is called creep. So for fatigue, I hear a catchword. What is that? Good. You better remember it. You note down also. So that whenever you talk about fatigue, the first thing that should come to your mind is cyclic loading. Okay. Other things you will study. Other things about fatigue you will study. Now when I say creep, immediately you must come back to the phrase time dependent strain. Creep means it is time dependent strain. Generally strain is not a function of time. In the stress strain graph, you know the strain is proportional to stress only. But the strain keeps on increasing over the period of time. This particular phenomena is called creep. Generally, creep is a phenomena observed at elevated temperatures. Creep is a phenomena which is observed at elevated temperatures. I'll give you an example. Suppose you have this incandescent lamp. Nowadays people, they don't use it. I keep the incandescent lamp under ideal conditions. There is no voltage fluctuation, nothing. Will the incandescent lamp burn forever? There is no voltage fluctuation. Why does incandescent lamp, the air fuse out? Why does it goes off? There is a tungsten element. Why does it tungsten element break? Imagine there is no voltage fluctuation. There is no disturbance in the vacuum. Even under ideal conditions, at elevated temperature, tungsten undergoes creep. And there is some time dependent strain taking place and it fades. So this type of failures, for example, the turbine blades. By turbine blades, what I mean is a turbine blade in a thermal power plant. A turbine blade in a thermal power plant will invariably fail by creep. A turbine blade in a thermal power plant will invariably fail by creep. Then there is something called fracture. Fracture is generally, it is also known as brittle fracture. It is a sudden failure associated with brittle materials. It is a sudden failure associated with brittle materials. Then you have corrosion and wear. These are other important sources of failures. Okay. Corrosion is another very strong phenomena. Okay. And in cities like Chennai, the problem of corrosion, because we are close to a shore. I don't know whether there is anyone coming from Dasan Nagar or in Dasan Nagar, the problem of corrosion is much more acute. Please believe me, the window grills in Dasan Nagar, they corrode much faster than in Tambaram or at Purvalli, because of the proximity to sea. The corrosion in Chennai is much more severe than corrosion in Madurai or Trichy or Viluppuram or any other place. Because of the proximity to sea, you have a very serious problem of corrosion, and this has to be reckoned with, this has to be planned for while you are developing a design. Wear is another. Wear is something which happens over a period of time. Again, okay, wear is associated with loss of material. Loss of material. Wear is not fatigue. Wear is something associated with loss of material. In Tamil there is a beautiful saying. Okay, which goes, Erumpura Kallum Puriyum. No, Kallum Teriyum or Kallum Puriyum. The Puriyum is a better Tamil word. Take it from me. Okay. See, as an ant walks, okay, it leaves its path in granite. By kal, what we say is a very hard variety of stone, which is granite. Okay, as an ant walks repeatedly over the same path, okay, a walk takes place in the granite. So, however hard the material be, when compared with granite, The ant legs are very, very soft. Believe me, it is not a comparison at all. But what happens? It is not one ant leg. It is millions of ant legs trying the same path over million times. You understand? So this makes some loss of material for the granite also. So this is what I want you to keep in mind when you talk about that. Even the material may be very, very hard. But when the run takes place over a long period of time, okay, the wear is very, very serious phenomena to be reckoned with. Is it okay? Now, another 5 minutes, I will give you a small introduction about the assignment that we are going to do. Can you please distribute it? Quickly go and distribute it. This is the third assignment. This assignment, for a difference, you will be working in groups of 4. And please believe me, you don't have a choice to form the group. I have already formed the groups. It is listed there. Number 1 to 4 will be one group. 5 to 8 another group. Okay. 9 to 12 another group. 13 to, okay, it goes on like that. So, oh, you got it? Only job, right. Listen here. So as part of the assignment, each individual will be given how many steps? For a group 50. Individual 50. கொடுக்க முடியுமா? So for a group around 100 to 200 pop sticks will be given to you. Pop sticks are nothing but your ice cream sticks. Flat ice cream sticks, you know. These ice cream sticks, you have paid already for it, so you need not give any money. But incidentally, some 48 people have not given the money. Second assignment. Okay, I am requesting the faculty member, you don't go behind you invalidate the assignment. Without paying the money, how can you do the assignment? So you can invalidate the assignment mark will be 0. So it is your responsibility. Sir, please don't go and ask them for money. You just invalidate the assignment, that is good enough. Let them have the thought, you don't mind. Now coming back to this assignment, you need not pay anything. You have already paid for this also. You will be given about whatever the remaining money we have, we will buy the pop sticks in large numbers and then distribute it. It will be roughly each individual will get about 50. You have to work among, listen here carefully, you have to work as a group of 4. You can elect one among yourself as a team leader, and each member must have a clearly assigned role, and that will be the first page of your assignment. Okay. Number 1, what is his role in doing the assignment? Number 2, so that must be spelled out in the first page. You have to write and then give. Who is the team leader? What are the works carried out by different members of the team? That must be spelled out very clearly. No. It is a report per team. It is a report per team. Okay. Similarly, bridge per team. As part of this assignment, what we will be doing is we will be designing. I emphasize the word again. We will be designing and fabricating a pop stick bridge. This ice cream stick bridge, we have to design and fabricate. The emphasis is more on design, and emphasis is also for planning to fabricate. I will explain. I will not do much. I will briefly explain what are the issues. You have a drawing given. Okay. That is the suggested. The shaded region is the suggested region of the bridge. Now what you have to do is, you have a river. Okay. The width of the river is 600 mm. The width of the river is 600 mm. Is there any mistake there? No. The width of the river is 600 mm. Okay. What you have to do is, you have to design a bridge to cross this river. You have to design a bridge to cross this river. The width of the bridge is suggested it can be 1 pop stick length. The width of the bridge can be 1 pop stick length. It can be bigger, but there is a constraint. The weight of the bridge should not exceed 400 grams. And please note, you will be evaluated based on the maximum weight that bridge can carry divided by the weight of the bridge. So you have an incentive to minimize the weight of the bridge. Okay, there is no point in making use of all 400 grams under making the bridge. At the end of the day, all the bridges will be broken. Okay, we will apply load and then we will break the bridges. Okay, the breaking load divided by the weight of the bridge, that will be the evaluation criteria. Okay, the best 3 bridges will get some certificates and awards also. Again, the emphasis is to design and fabricate. Please don't reduce it to a school exercise wherein you do some funny project to stick something together. There must be some clear, rational, thinking, scientific explanation for the shape you are in. Is it okay? So, and also there is going to be a lot of difficulty in fabricating it. Suppose, and please note, for all the joints you must use standard Fevicol only. Standard stationary Fevicol, that Fevicol you get used. No super glues. Okay. I cannot check, but I leave it to you. Okay. But the point is, how are we going to fabricate? You require some special fixtures to fabricate. How you are going to make the joints? These things you must describe in your assignment. Let it be a technical report. Okay. But also, no other material shall be used. Only the pop sticks that we supply, they have to be used. No other material. The pop stick is the beam. You have to make a beam out of the pop stick. Believe me, there are records where such a pitch can take up you do your mind, you can design a bridge which can take up 500 kg. Literally, 5 people can walk through the bridge. Of course, there won't be enough space to walk through, but that much load it can take. If you design it with care. I leave at that. Alright. With 01 to 04 is one team. 05 to 08 is another second team, another team. 09 to 012, I mean 012, 12 is another team. 13 to 16 is another team. 13, 14, 15, 16, one team. 17, 18, 19, 20 is one team. If there are some numbers missing, they are unfortunate, we cannot help. It will be a 3-member team. That is why I said it is only maximum of 4 members. If there are only 2 members, you can approach us and sort it out. If there are only 2 members in any team, you can approach the faculty, they will sort it out. Any other doubts? Now, one minute. I have another important agenda today. Okay. On March 26th, something important to technology has happened. Okay. Mr. Shivakumar has a nice video about it. It will go for another 15 minutes. You have to sit and listen. It starts now.
6,000 feet below the surface, and we're going to take a couple of them for a ride so that they can experience what from camera is seeing and experiencing as it descends to this alien ball.
Please believe me, it is roughly about 11 kilometers. The pressure of the water itself is 100 megapascals. The mild steel I told you, low carbon steel, it will get crushed at 300 megapascals. In whatever shape it is, it will get crushed at 300 megapascal steel. And the pressure itself is, the water pressure itself is about 100 megapascal. It is a very difficult issue. Okay, they have created a spherical structure. Of course, he has another video which talks about it. A spherical structure. The wall of the structure itself is about 62.5 mm thick steel. It is a special steel, not low carbon steel. It is a special steel. And if something happens, if the structure collapses, the human being will get crushed like a mosquito. Under the water pressure itself will get crushed like a mosquito. So it is a heavy risk. The design of the deep sea Challenger. It is worth looking into. Okay, and it happened. All the detail has not come on the web yet. It happened just few days back. The feat was completed on 26th March. Okay, it is the director of the Titanic. Okay, many have identified. Okay, so, but it has happened only few days back. The details are yet to come on the net. Okay, please look out and see the design aspects of the whole issue. Next video please.
The perfect shape made of strong, heavy material, a steel sphere. This epic dive has been done only once before by the truest expedition of 1960. Then and now, this simple structure is the only way to go for getting human beings to the bottom. We're constrained by the amount of pressure to a very small sphere in order to just have the vehicle light enough that we can even get it into the water and back on a ship. On the truest trip, that meant the two-man crew had to operate in a working space smaller than a phone booth. Cameron's journey won't be any more comfortable. The steel sphere is more violent firefighters. The space is tiny. Cameron will barely be able to move further than 9 hours as he pilots the craft to the bottom and back. He actually took a helmet to help get more movement. A sphere is still the safest place to be at the bottom of the ocean. The design hasn't changed much since 1960. The technology of the craft that gets it down there is a very different story. The Trieste voyage was groundbreaking, but the craft itself was limited. It took so long to get down, the crew could only stay on the bottom for about 20 minutes. Cameron said it is state-of-the-art. Its vertical orientation allows for a much faster descent. We'll be able to explore the bottom for over 6 hours, filming and collecting samples of this unknown environment like never before.
No, I strongly advise you go through the information on this. There are many engineering problems associated with it. I'll just say one and then leave it. One of the big problem was you reach 10 kilometers down. Okay, to come up, what you have to do is you have to shed some weight. So there were steel plates attached to the deepwater Challenger. These steel plates have to be released. Then your weight gets reduced. Because of buoyancy, you will slowly come up. But suppose, if these weights, if there is some problem in the release mechanism, what will you do? You cannot come out and release it. It is such a simple problem. Some plates are attached to the side. These plates are to be released. If these plates are released, the thing will come out automatically. But what if? Always the designer must ask the question, technique which will corrode the straps, thereby releasing it after some point of time. You strap it with some material which will get corroded. So even if this device fails, because these people can stay inside only for 24 hours. I mean, this individual can stay inside for 24 hours. Oxygen, everything is planned only for 24 hours. After that, there is no oxygen, you cannot come out, nothing can be done. So these straps have to be corroded and the plates have to be released anyhow. Okay, so that much of engineering has to go in. It was designed and fabricated over 8 years. Okay, I implore you strongly, you go through and then get as many details. Probably you can benchmark again. There are 6 competitive projects which are going on. And this man won the race. There are 6 designs which were currently going on to achieve the same thing. Okay, you can benchmark the various designs. These details are available on the public domain. Is it okay? Okay, thank you.